A collision, broadly put, is a strong but short-term interaction between objects. Now, before we write down the equations that describe collisions, I'd like to first, in this video, look at a graphical illustration of a two-body collision, that is a collision between two moving objects. So, okay, there's a lot to discuss here. Not to worry, we'll be taking it piece by piece. I want to show you this illustration here. Here's like a top-down bird's eye view of two objects, A and B here, the yellow and the orange, coming together, colliding briefly, and then moving apart from each other. So I want to discuss all this in terms of vector diagrams before we get into the equations. So one of the most important ideas is that during the collision itself, during that brief amount of time when the two objects are in contact with each other, they're exerting forces on each other, equal and opposite forces according to Newton's third law. So if we were to graph the force that B exerts on A versus time, and the force that this would be the force on B due to A versus time, and the force on A due to B versus time. And in fact, just the x components of those forces, that's what I'm graphing here. We would see that those forces are generally complicated functions of time. It's not a simple linear or quadratic function. It's something more complex. And so that suggests to us that trying to analyze the details a fraction of a second at a time of the brief collision would be challenging. So we have a better way of analyzing the outcomes of collisions. If we use momentum ideas, if we use in particular the conservation of momentum, we can compare the before state of the collision to the after state of the collision and not worry about the complex details of exactly what happened during the fraction of a second when they were in contact. So momentum conservation becomes our primary tool for studying collisions. And indeed, knowing the initial state before the collision, we can use conservation of momentum to predict the after state. We can predict the outcomes even without knowing exactly what happened during the brief time they were in contact with each other. So, momentum conservation. So what we'll be using. In all these diagrams, I've drawn them all in terms of momentum. So I just want to remind you that momentum and velocity, those two vectors for an object, will be parallel to each other. So all velocity vectors here are parallel to the momentum vectors. And we'll be considering this collection of objects A and B to be a system. So a system consisting of objects A and B. And if we state Newton's second law for a system, in terms of momentum, we know that the time rate of change of momentum depends on the presence of external forces. So suppose here in this example that there are no external forces between our two masses. There's just A and B pushing on each other while they're in contact, but that's it. And so if there is no net external force on our system, then dp dt is zero. In other words, the momentum of the system is a constant this entire time, meaning the velocity of the center of mass, the velocity of that imaginary point that represents the sort of mean position of the masses of the system, that velocity is also constant. Now let's talk more about that, the center of mass in this picture. Okay, here are A and B in their initial state. Say it's some initial time 1 here. And B looks like it's a little bit more massive than A. B has mass 3m, A mass 2m. So if I draw a line, this pencil line connecting the centers of A and B, somewhere along that line would be the center of mass of this system. And if B is a little more massive than A, then the center of mass, this pink dot, is a little closer to B than it is to A. Now, if there's no external force, then that pink dot, which will move as A and B move, the center of mass, this imaginary point, it moves as well. But if there's no net external force, the velocity of that center of mass will be constant. And so if you can imagine, as A and B move and come together and hit and then move apart, that whole time, this dot here, this imaginary point, will be moving in a straight line with a constant steady velocity all the way up to, during, and past the collision. no matter what A and B are doing, that dot right there, that center of mass, continues to move with a constant velocity. Kind of like Newton's first law. If there is no external force, then the center of mass cannot accelerate. It continues to move at a constant velocity throughout this whole story along that pink dotted line that I've shown in. So that's the trajectory of our imaginary point, the center of mass, moving with this constant velocity. Okay, let's look at the momenta of A and B themselves. So A initially has this momentum, we'll call it PA1. B initially this momentum, PB1. So their velocities are also parallel to those vectors, so they'll come together. And since they're not point masses, they're going to collide as soon as their surfaces touch. So they come in contact here, and I'm showing the forces that they're exerting on one another. Force on A due to B, and the force on B due to A, and by Newton's third law, those forces are equal and opposite. But those forces are going to be complex and changing with time during that fraction of a second they're touching. So actually, these vectors I'm indicating here would be the average force on A due to B during this time interval. And likewise, the average force on B due to A during that time interval, since the forces would be time dependent. But at each and every moment, they're equal in magnitude. So in these two graphs, I'm intending to show that the graphs are sort of mirror images of each other, just flipped over that horizontal axis, because the force on B due to A is equal and opposite to the force on A due to B at every moment. These are just the x components. There would be another set of graphs for the y components. You can see that those are also equal and opposite. After the collision, B and A start heading off in new directions, and I've got B's final momentum, PB2, and A's final momentum, PA2. So you see they have each changed in momentum. So these are their positions at some later time. I've drawn another pencil line connecting their centers, and so somewhere along that line is the center of mass, and again it'll be closer to B than to A, so there's the center of mass. Still lying along that pink dotted line trajectory that imaginary point has been cruising along this entire time. All right, so we've seen the before state and the after state, and we know there's this complex business going on during the collision itself. Let's compare the total momentum before to the total momentum after. And by total momentum, I mean the momentum of this system, P-sys, we can call it. So down here, I'm showing the total momentum of the system before the collision. That would be the momentum of A beforehand plus the momentum of B beforehand. So PA1 plus PB1. So this vector here plus that vector there, line them up head to tail, and the sum points from the beginning of that chain to the end of that chain. So here in light blue is a vector representing the total momentum of the system before the collision. And we've argued that the total momentum of the system should be constant if there's no external forces. So this light blue vector here should in fact be the constant value of the momentum of the system the entire time. So if we look at the vectors after the collision and add the total momentum here, PA2 plus PB2, so PB2 plus BA2, add those, draw in the vector that points from the beginning of the chain to the end of the chain. That's the total momentum of the system after the collision. We see indeed that it has not changed. So although A and B, their individual momenta changed, A's momentum changed, B's momentum changed, the total momentum of the system did not. So I could even draw on here the momentum of the system at this moment, treating the center of mass like as if it were a point mass containing all the mass of the system, like as if this were a point mass of mass 5m traveling in a straight line along this pink dotted path with a momentum equal to the total momentum of the system. So it looks like that is about 8 units over and 4 units up. 4, 5, 6, 7, 8. Going back to there. So there, that vector represents the momentum of the system before the collision. And that's also the momentum of the system after the collision. It was conserved. So here is the center of mass at some time after the collision. We could again draw in the total momentum of the system, and it would be 8 units over, 4 units up. So that vector would be our momentum of the system after the collision, which has been conserved. So that didn't change, although the momentum of A did change and the momentum of B did change. Let's look at those changes in momentum that did occur. A's momentum initially was only in the x direction. Afterwards, it was only in the y direction. And then B's momentum initially was up like this, up and to the right. Afterwards, B's momentum is just to the right. So down here, I want to show the change in momentum for A and the change in momentum for B. So delta P for A, that's A's final momentum minus A's initial momentum. So PA final minus PA initial. So that's PA2 minus PA1. And if I want to subtract PA1, I add the opposite of PA1 to PA2. So that's what I've done here. I've taken PA2 and added to it the opposite of PA1, drawing the sum from the beginning of that chain to the end of the chain, and this yellow vector is the change in momentum of A, pointing up and to the right, up and to the left. Now for B, I can construct the same thing, the change in momentum for B, B final minus B initial. So here's B final, here's B initial, so I can take this vector minus that one, meaning I take the opposite of this one and add it to that one. So here's PB2 plus the opposite of PB1, and the sum of those is the vector pointing from the beginning of the chain to the end of the chain. That's delta PB, the change in momentum of B, and that's this orange vector here. And I want you to see how the change in momentum for A is equal and opposite to the change in momentum for B. This is key. If the total momentum of the system didn't change, then whatever momentum A lost or gained was transferred to B. So the total stayed the same. So the change in A is equal and opposite to the change in B. Furthermore, and if you compare the directions of these two vectors, change in momentum for A pointing up and to the left like that, and look back at our diagram during the impact, delta P for A points like this, which is exactly parallel to the average force on A due to B. This force points in the direction of the change of the momentum. It's the force acting over time, acting over this short time interval, that's responsible for the impulse that changes the momentum. So our impulse points in the direction of the average force, that points in the direction of delta P for object A. And likewise for object B, it's delta P points in that direction, which is parallel to the average force on B during that time. The average force acting over this short time points in the direction of the impulse on B, which points in the direction of the change in momentum of B, delta P for B. We've discussed that before here with Newton's second law written in sort of impulse momentum theorem form here, this set of vectors. We've argued that the net impulse on an object points in the same direction as the change in the momentum of the object points in the same direction as the average net force on the object and the average acceleration of the object during some short time interval, or during any time interval. That's why we've got this vector here parallel to the average force vector right there. Okay, and those vectors are related back to this graph up here. The area under this force versus time curve, that area represents our impulse. So this area would be the change in the momentum of A, x component. Oh no, this is the force on B, my mistake. So this is the change in the momentum of B, x component. And this area here, that impulse would be the change in momentum of A, x component. Note that this is negative, this one's positive. A's momentum had a negative change in the x direction. B's momentum had an equal but opposite positive change in the x momentum. So indeed, those two areas are equal and opposite to each other. The impulses are equal and opposite, just as these delta p vectors are equal and opposite, just as the average forces on them are equal and opposite, all coming from Newton's third law. Okay, next we can discuss the equations.